Hello there. Now we're going to take a closer look at the complex roots case for our characteristic polynomial for the second order linear differential equations with constant coefficients. So just to recall that we are looking at equations of the form y double prime py prime plus qy equals 0. And for this case, we're looking at when p squared minus 4q is less than 0. So that is from our characteristic polynomial. So we had shown that our characteristic polynomial for these second order linear differential equations look like lambda squared plus p lambda plus q equals 0. So we can see that when we try to find lambda using the quadratic formula, we get minus p plus or minus the square root of p squared minus 4q all over 2. And the p squared minus 4q is our discriminant. So when that is less than 0, we have a negative under the square root. So we end up getting complex roots. Okay, so if we end up solving for these complex roots, we're going to get that the roots are going to be of the form a plus ib, and that plus or minus from our quadratic formula is going to tell us that the second one is just the complex conjugate. So complex conjugate is often written as just a bar over the variable. So if lambda is our complex number, the complex conjugate is written as line over lambda, and that just takes any I to minus I and vice versa. So we showed that the solutions are going to eventually look like y of t equals a1 e to the at cosine bt plus a2 e to the at sine bt, but it wasn't very clear how, knowing that when we searched for our, when we had real solutions to our characteristic polynomial, so for the real case, our general solution looked like y of t equals e to the lambda 1 t with some constant out in front. So I'll just say a1 here, plus b e to the lambda 2t. So it's not very clear how we go from this this method, this case, to getting sines and cosines. And the sines and cosines aren't just coming from nowhere, they're coming from somewhere. So let's take a look at how do we actually get those. So if we follow the same sort of logic that we did for the real case, we can say that solutions look like z of t e to the lambda t. In this case, lambda is the complex number, so e to the a plus I b all times t. And that will be my z1 for now, I'll just say. And then z2, which is lambda bar of t, is going to be e to the a plus, minus ib times t. So just some quick notes here. One thing that we can notice is that the first solution and the second solution are also complex conjugates because we just, it's the same solution, but just switching that I to a minus I. Second thing that you'll notice is I'm not using Y here. The reason why I'm not using Y is because this is just convention in math and a lot of like physics and engineering courses, where X and Y are typically real numbers. Z is often used if we're not talking about third dimension, but Z is often used for complex numbers. So we can see that this solution, Z of t, solutions here are complex. We have i's in them, we have imaginary numbers in them, so they're complex. And a lot of times we want real solutions. So while these two are solutions, and you can keep them as solutions, we want to look for real solutions. Real solutions. So I'm going to reserve y of t to be my real solution. And that's ultimately the solution that we're going to want in the end. So now I'm going to rewrite my z of t. I'm going to use this property of exponents, where if I have some sum or minus in a exponent, I can break this up as a product of exponentials, IBT. So similarly, I have this complex conjugate here, IBT. Okay, so now we're going to use a formula that is going to come up a lot, and it's a super useful formula. And you might have seen it before, but maybe you're not as familiar with it. And this is called Euler's formula. So, so Euler's formula is how we end up getting this connection from our exponentials to our sines and cosines. And Euler's formula tells us that e to the I theta is going to be the same thing as cosine theta plus I sine theta. So keep this in mind. It's going to come up in a few different places. So here we can see that this first exponential in both these cases are real, and that's good. Because that kind of matches with that solution that we ultimately got. So then the second exponential, I'm going to break this up as cosine theta plus I sine theta, and sorry, not theta. I'm looking at my Euler's formula written out, but this is cosine bt plus sine I sine bt, and cosine bt minus I sine bt. And you can see again, we're still, our two solutions are still complex conjugates of each other. Nothing very, different is happening there. One thing we want to check, so we want to check if our solutions, are they linearly independent? So in order to check that, we want to make sure that they're, are they not constant multiples of each other? If they are, we have a problem, and we need to think of some other sort of solution. But let's check before we start, worrying about what other solutions we might have. For the sake of checking if they're constant multiples of each other, I'm going to just deal with the exponentials and not the sines and cosines, just because it's going to be a bit easier. So I have e to the at times e to the I bt over e to the at e to the minus I bt. And I can see that the e to the at's cancel out. And I can combine my e to the I bt and e to the minus I bt as e to the 2I bt, which is a function of t. So that means that it is not a constant multiple of each other, which means that they are linearly independent. Okay, good. So we have our two linearly independent solutions. I'm going to say that we can add these solutions together. I'm going to use y for now as our complete solution. And you may say we can just stop here, but the issue still is that z and z bar are imaginary, or they're complex numbers, and we still want to have solutions that are inherently real. So for real valued solutions, we can rewrite z of t and z bar of t as follows. So we know that z of t is going to be this e to the at cosine bt plus I e to the at sine bt. And similarly, for our complex conjugate here, we have the same thing but with a minus, I e to the at sine bt. So what we can see here is that we can rewrite this as a y1 of t, and then plus I y2 of t. This one on the bottom is going to be y1 of t minus I y2 of t. And that is only going to work if we take y1 of t to be e to the at cosine bt and y2 of t to be e to the at sine of bt. So we can then rewrite our solutions, our complex solutions here as z of t equals y1 of t plus I y2 of t, and similarly z bar of t equals y1 of t minus I y2 of t. And we can notice that y1 and y2 are both real valued functions. So that's good. We're making some progress. So another way to look at this is to say that y1 of t is just the real part of z of t, or the real part of z bar of t. That's the same thing here, which is that e to the at cosine bt, and y2 of t equals the imaginary part of z of t, or z bar of t. The imaginary parts are the same. Okay. So sometimes if we want to, write our solutions y1 of t and y2 of t as, as a function of z and z bar, we can write it a particular way that isn't really going to come up in this class, but we can see that if I take 1/2 of z of t plus z bar of t, we can see that we're going to get this y1, and I'll do this out. So 1/2 our z of t was e to the at cosine bt plus I sine, plus I sine bt, and then our z bar was e to the at cosine bt minus I sine bt. So you can see that our cosine terms are going to add up, and our we're going to get a factor of 2 in front, and then our sine terms are going to cancel out. And when that happens, we're just going to get e to the at cosine bt. And if we want to come up with our second solution as a form, as functions of z and z bar, we actually have 1 over 2i z of t minus z bar of t. And similarly, when plugging this in, we're going to see that one of our terms is going to add up and the other term is going to cancel out. So b of t plus I sine b of t minus e to the at cosine b of t minus I sine b of t. So we can see that there's going to be a positive cosine and a negative cosine, so they're going to cancel, and then we get a positive I sine bt, and this negative are going to make this positive I sine bt. So we end up getting 2i over 2i, which will cancel, and we will get e to the at sine bt. All right, so we showed that we can massage our original complex solutions that we had, which we got the same way that we got our solutions when we had real roots. We just plugged it in using the same thing, and we showed that we can rewrite that to get sines and cosines, and ultimately, since we know that that's a linear combination of a solution is a solution, we use the fact that I can define my y1 and y2 as linear combinations of those two solutions. So I'm just adding those complex solutions together, and I have some constant out in front. For one of them, it's 1/2, and one of them, it's 1 over 2i. And by doing that, I made two solutions that are real. So I ended up getting 2 real valued solutions, which ultimately are my y1 of t, which is e to the at cosine bt, and my y2 of t, which is e to the at sine of bt, for characteristic root of the form a plus ib. And we're done.